Thanks for the introduction. So generative adversarial networks are a relatively recent approach to modeling data in high-dimensional spaces. This is an invited talk, and I'll be talking about generative adversarial networks in general. I won't just be talking about my own work. So to make it clear whose work I'm presenting up front at the start, I'll be talking mostly about these 4 papers on this slide. And I'm a co-author on 2 of them, but I'm not on the other 2. Also, a lot of these slides were developed along with Aaron Corville. We both speak about this subject a lot, and so we've passed each other's slides back and forth. So the basic idea of what we're trying to accomplish with generative adversarial networks is to make a generative model, and specifically it's a model that can draw samples, but we actually don't necessarily have any way of evaluating the probability distribution that it represents. So this is the most simple version of the generative modeling task you could think of. We have a bunch of samples from some distribution that the data is drawn from, and we want to make a model that can draw more samples from that same distribution. On this slide, I'm showing you an example with the train and the test set of TFD. If our generative model were actually working, we would like it to be able to generate the same things as we have in the test set on the right. So far, we don't have anything that quite accomplishes this goal, but this is the idealization of what we'd like to do. One question that you might have is, why do we want to do this? A lot of people understand why you want to make a model that actually gives you the PDF of the data, but it's less clear why we might want to be able to draw samples from that distribution in the absence of knowing the PDF. One reason is that a lot of tasks that we want to solve can be cast as conditional generation tasks. This includes pretty much any distribution where the output is multivariate and has some kind of rich structure to it. Most of the time that we do supervised learning so far, we've tackled relatively simple problems where it's just classification or regression. You get an image and you say what category it belongs to, or you estimate some number. But in many tasks, we actually want to output some kind of structure that's just as rich as the input. For example, in speech synthesis, we want to type in a sentence and then have the computer emit an audio waveform that actually contains a spoken version of that sentence. Or for text translation, there are many possible translations even when you map from text to text. And we'd like a model that can realistically emit any of these possible translations instead of obviously emitting only the same value for each input. Another reason we might want to have generative machines that can sample from a distribution is that we can use them to generate training data for other kinds of models. For example, if you have a reinforcement learning model, you might want to train a generative model that can draw samples from experiences that it has. And that way you can train an agent on simulated experiences where you don't need to worry about the agent being damaged by doing dangerous actions in the real world. You can also use an environment simulator for planning. When you're trying to choose which action you can do, you can just simulate several possible actions and then choose the one that gets the best reward on average. Finally, training these generative models might actually help us to leverage unlabeled data. We haven't actually demonstrated that this actually works yet, but you could imagine that some of the internal representations of the generative machine could be useful as features for a classification task. So far, the way that people have trained generative machines is usually to train a generative model that actually represents the probability distribution, and to fit this model using maximum likelihood. So you just write down some formula P of x parameterized by vector theta, and you do gradient-based learning to maximize the log probability of the training data with respect to the parameter vector theta. Until a few years ago, the most popular way to do this was with undirected graphical models. And in the context of deep learning, the flagship undirected model is the deep Boltzmann machine, where you define an energy function over the visible units and several layers of hidden units. Here, the basic idea is that you define an unnormalized probability distribution by taking e to the negative energy function. And that energy function has no constraints on it. Taking e to the power of the negative energy function turns it into a positive function. And then you can normalize that by dividing by the sum over all possible states in order to obtain a probability distribution. That formulation gives you a lot of freedom in how you can specify the energy function itself, and then you're still guaranteed to get a probability distribution at the end. Unfortunately, computing that normalizing constant is NP complete, and our ability to approximate it is limited. In particular, if you train the Boltzmann machine well enough to start to represent a sharp distribution with widely separated modes, then our ability to approximate it decays. Our best approximations to the partition function are based on drawing samples from the model using Markov chain Monte Carlo. And these Monte Carlo methods work very well as long as we're able to move between the different modes. As the modes become sharper and better separated, we have a more difficult time transitioning between them. In this example here on the MNIST dataset, you can see how we learn different features for different pen strokes in the data. And you can imagine that when you sample the latent variables given the input, they're going to do a very good job of encoding exactly which pen strokes are there. So if you sample the hidden units conditioned on this 1 here, they're going to represent very well that there's this 1 pen stroke in the middle of the image. And then when you sample the visible units again, they're going to recover something that looks very similar to that 1. You're going to have a hard time sampling the hidden units and then sampling the visible units and getting something that looks like this 9. So there are a lot of strategies for increasing the temperature of the distribution temporarily in order to force the Markov chain to mix. But we don't seem to have entirely solved this problem to our satisfaction. Because Markov chains and undirected models seem to have a lot of problems, a lot of people have also turned to studying directed graphical models where a similar problem arises. In this case, rather than needing to sum over all possible states in order to compute a partition function, we need to sum over all possible configurations of the latent variables and evaluate the posterior probability. Once again, this summation is also intractable. The main way that people have solved this is to use variational learning. And right now, probably the most popular deep directed model is the variational autoencoder. I won't go into a lot of detail about this because plenty of other people here are speaking about it, but I'm going to recap a few things that are important for comparing to generative adversarial networks. The basic idea is that you have a distribution over the hidden units, Q of Z, and we can draw samples from this distribution by using a neural network and some noise. So we have an input, X, that came from the data set, and we run X through a differentiable encoder, and we supply some noise, and together those give us an output, which is a sample from the approximate posterior over the latent variables. You can then run a differentiable decoder from this sample of the latent variable Z and get the expected value of X given Z. And if you want, you can also get parameters for the variance around it and things like that. This basic idea of a differentiable decoder, or as I'll call it in this speech, a generator net, is very widespread, and there are several different approaches to training generative decoder nets available right now. They will be present in generative adversarial networks, so it's important to understand exactly how you set up the learning problem for training the generator net. And I'll come back to this later and describe how the two frameworks are similar and different. One other related method that's worth mentioning is generative stochastic networks. These networks learn the transition operator of a Markov chain, and they're probably the most similar thing to generative adversarial networks. The basic strategy is to give up on having an explicit representation of the distribution P of X and just generate samples, which is the same thing that generative adversarial nets do. In both cases, you can do some post-processing to recover the distribution itself if you really need it, but that's not the core of the learning algorithm. One of the main drawbacks to generative stochastic networks is that it can be very difficult for your Markov chain to mix from one example to another extremely dissimilar example. So here in this hypothetical situation, it might be easy to mix between these faces from the TFD dataset, but difficult to mix to this face, which is widely separated in terms of the values that occur at each pixel. So the basic idea of generative adversarial networks is to learn a sampling mechanism, but to learn it for the generative differentiable network setting, where we're just doing ancestral sampling in a directed graphical model. Basically, we're just going to learn to generate some input noise from a fixed prior distribution and then transform that noise into data space. The advantages of this over the generative stochastic network is that there's no Markov chain involved, so there's no issue with mixing. And the advantage relative to variational autoencoders is that there is no variational lower bound. There are also some disadvantages associated with the method that I'll describe later. So the question is, how can we do this? How can we actually train a differentiable generator net without a variational lower bound? And in order to do that, we're actually going to bring in some ideas from game theory. The basic idea of game theory is that you have a scenario with more than one player, and each of these players has a set of possible actions that you define formally. Each action is also associated with a set of possible outcomes, and you define the mapping from actions to outcomes formally as well. These mappings from actions to outcomes can be stochastic. Additionally, there's a reward for each player associated with each action, and each of the players tries to choose their actions in order to maximize their own reward or the value that they get from the game. The important difference between game theory and optimization is that each player cannot control the other players. So when we simulate the game as a whole, we're looking for an equilibrium situation where no player can improve their reward by changing their own strategy. But if you were able to jointly control all of the players' strategies, then you might be able to increase or decrease some of their rewards. The simplest version of a game theory setup is the two-player zero-sum game, and we're going to formulate the simplest version of generative adversarial networks as this kind of game. The idea of this game is that your opponent's winnings and your winnings always add up to 0. So your opponent's winnings are the negative of your winnings. This is an especially simple kind of game because you don't need to think about whether you're going to cooperate with anybody or not. When there are multiple players or when your winnings can combine additively, then you can think about whether you want to form a coalition with some subset of players in order to beat another subset of players. Or even when there's just one other player, you can sometimes decide whether you want to trust them and cooperate, or if you don't trust them and you're just going to do the worst possible thing from their point of view. In the two-player zero-sum game, you know there's only one other guy, and you know that you can't trust him. And so you just try to grab the most for yourself as you can. And that kind of scenario is a lot easier to analyze. In particular, there's a theorem called the minimax theorem that says there's a rational strategy for both players for all finite two-player zero-sum games. In our case, we're using a continuous game, so there's infinitely many strategies, and the minimax theorem doesn't apply. But we'll show you that we can prove a special case of the infinite game minimax theorem that applies to generative adversarial networks. So the way that you design and analyze a two-player zero-sum game is based on formalizing a strategy for each player and looking for an equilibrium. In order to find an equilibrium, you might need to consider the possibility that each player chooses their actions at random from some probability distribution. And that's called a mixed strategy. And if you find an equilibrium involving mixed strategies, it's called a mixed strategy equilibrium. So one example is the game of rock, paper, and scissors. If we say that the player who wins gets a payoff of 1, then the player who loses must get a payoff of -1. And the only way you can find an equilibrium in this setting is for each player to choose their action uniformly at random among rock, paper, and scissors. If one player said, for example, I'm always going to play rock, then the other player could say, well, I'm always going to play paper. And then the player who always plays paper would win. So the player who's always playing rock would have an incentive to change their strategy. At the mixed strategy equilibrium where everybody chooses their actions uniformly at random, neither player can improve their expected payoff without also changing their opponent's strategy. To set up the game specifically for adversarial networks, we're going to consider a game between two players. One of them is what I'm going to call the discriminator network, D, and the other one is going to be the generator network, G. The generator network, G, is the same thing as the decoder in the context of variational autoencoders. The idea is that the discriminator network D is trained to recognize whether a sample comes from the data or from the generator network. And the generator network tries to trick the discriminator network by generating samples that are hard for D to distinguish from the data. Here's the schematic that shows exactly how we connect these different networks. On the left, I show what happens with the training of the discriminator net. We have a data set containing several images from the training set X, and we just sample those uniformly at random and then run them through the discriminator net, which is any kind of parametric differentiable function in this context. The discriminator net then outputs a number between 0 and 1, giving the probability that it believes that this input came from the data set. And we're going to train the discriminator net to try to output 1s every time that these x's are drawn from the data set. Simultaneously, we have another half of the training algorithm, which is drawn on the right. In this other half of the learning algorithm, we first draw input noise from some simple distribution over z. So this is just our prior over the latent variables, and this prior never gets adapted during training. Usually this is just going to be something like an isotropic Gaussian, and you want to choose the size to be based on whatever you think the intrinsic dimensionality of the data is. So in most of the experiments that I'll show you, we had an isotropic Gaussian over 100 random variables. We then run the noise through a differentiable function g that maps the noise into the data distribution. And we want this to essentially be a continuous random number generator process so that we can backprop through it. After we've got our sample from the data, or our sample from the model that's intended to look like the data, we can run it through the discriminator net. And again, it outputs a number between 0 and 1. This is where we start to see that we have a game theory setup rather than an optimization problem. Using the values that we propagated through both the generator and the discriminator in the right half of this slide, we then train the discriminator to try to output a 0, and we train the generator to try to make the discriminator output a 1. So we compute the same gradients for both models, but then we do gradient ascent on one and gradient descent on the other. This is the formulation of that game in terms of a value function that the different agents try to maximize or minimize. And you can see that the form of this value function is as it's a log likelihood for a binary discrimination task. So specifically, it's the discrimination task that you get when you create a data set containing 50% real data and 50% samples from the generator. And you assign labels that tell the true origin of each example. This is actually the same function that arises in noise contrastive estimation, if you're familiar with that technique. The difference is that noise contrastive estimation is learning a model that is used implicitly to define the discriminator, and here we're learning the generator. Another difference is that in noise contrastive estimation, the generator is fixed, and here the generator is the thing that we're actually adapting in order to learn. But this function itself has been used before in other kinds of generative modeling tasks. So you can analyze noise contrastive estimation theoretically, and it turns out that it has a close connection to maximum likelihood. Specifically, maximum likelihood is noise contrastive estimation modified such that the discriminator's beliefs about the data distribution are copied into the generator network at every step. Noise contrastive estimation is computationally cheaper because it doesn't actually ever update the generator. And you can show that because it never updates the generator, that it's failing to obtain the same asymptotic error rate as maximum likelihood. We don't actually know very much about how generative adversarial nets compare to maximum likelihood. They are actually updating the generator in this, similar to how maximum likelihood does, but they use a different update rule for it. We know that at every step, if the discriminator is optimal, it's going to take on this particular form, or at least when you have a parametric family over the discriminator, it's going to be as close as possible to this. Specifically, it's the ratio of the probability of the data divided by the probability of the data plus the probability of the model at the current x point. Keep in mind that we don't actually know the probability distribution over the data. That's why we have to learn it. So you can't actually plug this formula into your computer and evaluate it and see how close your discriminator is to it. But we know that your discriminator should be converging to this value. Once you have the discriminator implementing that ratio, you can see that it helps to guide the generator to learn the correct function. This is a cartoon of how the learning process learns. Initially, you have a poorly fit model, and I'm drawing a one-dimensional representation of how it works. We have one number line representing Z space, and another number line representing X space. For a real model, these are going to be multidimensional, but in order to show you on a slide how it works, I've drawn them as one-dimensional. The generator net implements a mapping from Z space to X space, and the way that it warps space controls the distribution over X space. In this case, where both Z and X are continuous, and if you restrict the domain to the 0-1 interval for Z, then you can think of the generator net as implementing the inverse cumulative distribution function over X. In higher dimensions and when the range of Z isn't bounded, then that interpretation doesn't quite apply, but it gives you the right intuition for what it's doing. So initially, you've got this mapping from Z to X, defining this distribution drawn with the green curve here over X space. And at the start of training, that distribution is not going to match the distribution from the data. Simultaneously, you've got this function d of x, which gives the posterior probability that each point is drawn from the data rather than the model. And initially, this won't be fit very well. After one step of learning, or probably after many steps, but for the purpose of the cartoon, we'll show it in one step, the discriminator will be fit to the current version of the generator, and it will implement that equation that I showed on the previous slide. So it's going to be high in areas where the probability of the data exceeds the probability distribution defined by the model, and it's going to be low in areas where the model's probability exceeds the data. So you can see over here it's high on the left and low on the right because our model has its Gaussian bump too far to the right. Next, we update the generator. And what this will do is everywhere that the generator outputs a point, we look at whether it should move left or right on this curve following the gradient of the discriminator. So all the outputs of the generator are going to flow uphill into areas where the discriminator believes that it's more likely for there to be data. And it's important to do this only incrementally. You don't want to completely optimize the generator in any one step. Otherwise, it would map all points into the mode of the discriminator, and that would prevent any more learning from happening because there wouldn't be any way to tease apart different outputs of the generator. We call that the Helvetica scenario, but fortunately it doesn't occur very much in practice. After you continue this process for a long time, you should eventually reach a mixed strategy equilibrium. At equilibrium, the generator net is going to match the data, and if you assume that the generator net has infinite capacity, then it should match the data distribution exactly, given enough samples. In practice, you'll get some approximation error from the function that you're optimizing over not being expressive enough, and you'll also get some generalization error from your training set not being infinite. If you do actually reach this perfect mixed strategy equilibrium, then your discriminator net is actually going to output 0.5 everywhere. It won't be able to discriminate data from samples because the two implement exactly the same distribution. And that means after you're done learning, you essentially discard the discriminator net. It's just representing a constant value of 0.5 everywhere. This process has some nice theoretical properties. If we assume that we're able to optimize directly over probability distributions, then there's one unique global optimum, one saddle point where no player can improve their strategy by changing to any other strategy if the other player has to keep their strategy fixed. And this saddle point corresponds to the location where the generator net has captured the true distribution. Moreover, if you're optimizing in this space, then convergence is guaranteed. Unfortunately, in practice, there's no guarantee that SGD will converge. So what I mean by SGD here is where you train the generator to minimize the value function of the discriminator, and you simultaneously train the discriminator to maximize its own value function. So you're doing gradient steps with opposite sign on the parameters of each model. This is a little bit different from what happens when we usually analyze a statistical estimator. Usually what we do is we have an optimization problem where we're minimizing a function, and we show that in function space, the minimum of our objective function corresponds to recovering the true distribution. And then we say, in practice, we're not actually going to have a non-convex optimization problem, but hey, we'll just get stuck in a local minimum somewhere, and it will hopefully be pretty good. In this case, we're actually not guaranteed to reach a critical point, and that makes it a lot more problematic than what usually happens when you move from convex to non-convex optimization. In particular, you can have a problem where the network oscillates forever. So this is a graphic that was donated to me by Alec Radford. He's showing what happens when you fit a Gaussian distribution with too big of a learning rate. And if you use the right techniques to force it to converge, you can get it to converge, but it can be a little bit difficult to figure out the right conditions to converge. I think this is an important open problem. I'm not an expert on game theory. I sort of wandered into this field after having the idea for generative adversarial networks. And I'm hoping that some game theory experts or people who choose to study game theory after hearing about these will come up with a better way of forcing convergence of the optimization problem. This is what samples from the model look like. When we visualize them, we plot a bunch of samples, and then we choose a few samples to compare to the training data set. When you look at samples from a generative model, it's very important not to just look at the samples and see if they look good or not. You also want to check and make sure that they're not just copying from the training set. It's possible to train a generative model that produces really nice looking samples, but then find out that those samples came straight from the training set. What we do here is we plot a bunch of samples, and then in the rightmost column for each plot, we show the nearest training example to the model sample on its left. In the case of MNIST, you can see that we've essentially solved this task. The model samples look to me basically the same as the true data. And when you look at the pairs where we check for matches against the training set, there are actually differences between them. For TFD, the faces are too blurry, but we can at least see that we don't seem to be overfitting because there's a lot of difference between the sampled faces and the nearest neighbors in the training set. For CFAR 10, we're very far from solving the problem. We don't seem to be getting the global structure of the image right at all. We are getting the idea that there should be a lot of interesting edges and corners and things like that in the data, but we're not really getting things that look like dogs or airplanes or horses. Also keep in mind, look at the training samples on the right. CFAR 10 is not a very pretty data set to start with. So the samples are never going to look all that great, but they should look a lot better than they are. One thing we can do that's kind of interesting is to look at the manifold that the model has learned and see how it's chosen to lay things out. This is a 2D manifold on MNIST, where at every coordinate in the image, we show what happens if you map that coordinate in Z space to X space. This model is a bit smaller than the ones that we usually use. This one was made specifically for the purpose of creating this visualization. So we trained it with only 2 units in the code. Usually we used 100 units and got somewhat better samples. One way that we can look at the properties of the distribution that we learned in higher dimensional spaces is actually to make a video where we interpolate between different positions. So the way that we make this video is we draw 2 different samples. I've indicated them here by A and B. After we sample A and then sample B, we make a video where we fly from A to B, and then we'll sample a third point C and fly onto that one. Because we fly in a straight line between different paths, but the model was trained sampling from a Gaussian, this is going to cause some kind of strange results. Specifically in high dimensional spaces, most samples from a Gaussian are going to live on a shell with relatively high radius, and then we're going to interpolate through regions that have lower radius. So this is going to show us the way that the model responds to a linear trajectory, but we're also going to force the model to go into an area where it hasn't been trained quite as well. So we do expect it to show us some kind of pathological things, but it will give us an idea of what the code elements of the model actually mean. On the left, you can see that as we fly around in linear trajectories in MNIST, that you actually, in most cases, see the ink move around. You do occasionally see ink pixels just vanish rather than translate, but a lot of the time we actually do see translation happening. In TFD, we see fairly smooth changes in lighting, followed by sometimes changes in the identity of the person or their expression and so on. We do seem to be getting changes that are semantically meaningful as you alter the coordinates linearly. For CFAR 10, it's not as successful. On CFAR 10, one thing that's kind of disappointing is you very rarely see things actually move, like we saw in MNIST. Usually when we change the coordinates in the manifold linearly, we see relatively linear changes in pixel space. In other words, we see components fade in and fade out, rather than translate around or rotate around. To me, that means that our z coordinates don't really represent the configuration variables, like the location of different parts, as much as we would like them to. It does make sense for there to be some configuration variables that represent the presence or absence of parts, and that can explain why we do see fading in and fading out. The thing that bothers me is I don't see many geometric transformations happening. So it would be nice if we could discover models that actually get those geometric transformations when you interpolate linearly in config space. So to compare generative adversarial networks and variational autoencoders, one thing we can say is that both of them use backprop through continuous random number generation. Another thing we could say is that empirically, both of them seem to have a big problem with underfitting. Underfitting seems to be the big problem in general with deep generative models right now. Not overfitting. The reason we can say it's not overfitting is that the samples do not look like the training data. If we were having trouble with a generative model overfitting, it would be the model just emits the same images that it was trained on. And we essentially never see that happen. We don't see that with any of the kinds of models that we train. And that suggests that optimization is really what we need to focus on. For variational autoencoders, I don't know for sure why they are underfitting. I suspect that part of the reason is that the variational lower bound might cause there to be some trouble. For generative adversarial networks, I think the reason for the underfitting is the non-convergence problem in the game theory setup that I showed you earlier. But we haven't actually been able to positively demonstrate that. And another important difference between generative adversarial networks and variational autoencoders is the order in which things are wired up has implications for the way that backprop works. Specifically, right now, we don't have a very good way of backpropagating through discrete variables. You can use the reinforce algorithm to backprop through discrete variables, but it's not nearly as good as the real backprop of continuous variables. For generative adversarial networks, the output is the data, and we need to backprop through that layer. And that means that we can't use discrete outputs. We can't use models of text and things like that very easily with generative adversarial networks. For VAEs, you need to backprop through the latent variables because the latent variables appear in the middle of the backprop graph. So that means that VAEs cannot use discrete latent variables very well. Generative adversarial networks can use discrete latent variables just fine. The only problem is you can't shape the distribution over the latent variables. But as long as you're okay with sampling discrete values from a uniform distribution or a sparsified multinomial or something like that, then you're fine. One idea that's still in progress but shows some promise is actually combining different objective functions from different generative modeling approaches. There's no reason that a generative network for a pair of generative adversarial networks can only be used in the context of that pair. So Alec Radford has showed me some projects that he's working on where he's actually combining the variational autoencoder objective with the generative adversarial network objective. Now this is still very preliminary work, so he thinks he can improve the quality of the samples quite a lot. But his thinking is that variational autoencoders on their own tend to produce somewhat blurry samples. Generative adversarial networks tend to get sharper edges and corners. Variational autoencoders don't have the oscillation problem that generative adversarial networks do. So you might be able to force convergence by including the variational autoencoder objective function in combination with the generative adversarial network game. There's another approach to training generator networks that came out this year. It's based on moment matching. And it's kind of ironic that this came out later because actually the way that we thought of generative adversarial networks in Yoshua's lab was on an alternative to moment matching. Yoshua was interested in training generator nets that would explicitly do moment matching on a finite list of moments. And I thought of the idea of having a discriminator network instead of a finite list of moments because I thought it would be difficult to enumerate enough moments to capture everything we wanted about the distribution. What we didn't know about at the time is that there's a criterion called MMD, which is basically kernelized moment matching. And 2 different groups have written papers this year about training generator nets by backpropagating through the MMD criterion. It's a little bit different from the generative adversarial network or the variational autoencoder framework because the objective function is not defined with respect to a single sample from the model. It's only defined with respect to a batch. So you have to draw a large group of samples and then estimate their moments and compare their moments to those from the data set. The samples on MNIST tend to have problems like missing pixels where the digits aren't completely connected together. And this seems to be a problem primarily with the MMD criterion itself, because in some cases, these models are actually setting the state of the art in terms of the MMD measure on the, by comparing the model samples to the MNIST test set. In general, we've seen that these generator nets, whether you train them with the variational autoencoder criterion or the generative adversarial network criterion or the MMD criterion, they don't really solve the generation task yet. They aren't, reaching the level of performance that we've been able to see with supervised neural nets. So the question is there something wrong with neural nets themselves, or is there something wrong with the way that we're training them? A recent paper that helps us answer this question appeared at CVPR this year. It's about generating images of chairs with convolutional networks. And here they are able to see how well a generator net can perform by training it in a purely supervised way. They use a computer graphics engine to generate images of chairs, given the configuration variables like the position, orientation, scale, lighting, and object type identity of the chair. In this case, they're able to use the standard supervised neural net training algorithms that lie behind all of the current human-level object recognition results that we've had with traditional neural nets. And in this context, they actually produce much nicer images than when we try to do the learning in a completely unsupervised way. So when you actually define the semantics of the Z space and you provide specific examples for how to map from Z to X, then generator nets are extremely powerful and essentially solve the task. But when we actually want to learn to model X space given samples only of X, and we have to have a training algorithm that also figures out how to lay out Z space and map from Z to X, then that's a much harder problem that we don't seem to have solved yet. One interesting thing about the generative adversarial networks game is that I presented it to you in terms of a 2-player minimax game where both players are fighting over the same value function. But in practice, we actually use a slightly more general game that's harder to analyze theoretically. The more general game has a different payoff for the generator than for the discriminator. And the reason is that in practice, this different formulation of the game gets better gradients for the generator. What I'm plotting here is on the x-axis, the discriminator's response to a generator sample. So when the discriminator gives a very high response, then it's saying it believes that this sample came from the data. And when it gives a very low response, it's saying that it believes that the sample definitely did not come from the data. That means that if the discriminator net gets to be too good and can readily identify samples as being fake, then as you can see, the blue curve on the left side here is essentially flat. And that means that the generator network has no real signal with which to learn. So in practice, what we do is we switch to this green curve here. Basically, what we do is, rather than trying to minimize the log probability of the discriminator net getting the right answer, we try to maximize the log probability of it making a mistake. And you can see that they're both monotonically decreasing as a function of the discriminator's response. So intuitively, they're trying to do the same qualitative thing, but they have very different bias and variance properties. Now, both of these are sort of ad hoc criteria that came from just thinking about intuitively how we want the generator and discriminator to behave. But there's a third criterion, which is also very flat on the left side and extremely steep on the right side. This function turns out to actually recover the maximum likelihood gradient in expectation. The problem is that it only recovers the maximum likelihood gradient in expectation. The variance of it is quite high. because in order to get very non-zero gradient, you need your sample to land over here in the region where the discriminator thinks that your sample is essentially real. And it's difficult to initialize the training procedure with this kind of criterion, because early on in training, your generator net is never going to produce anything that looks very similar to data. So it's always going to be landing in the extremely flat region on the left. And theoretically, if you could draw an infinite amount of samples, you would get some over here and get the right expected gradient. But in practice, that's such a black swan event that you just don't actually see it happen. There's some interesting extensions you could do to the generative adversarial networks framework. One limitation that generative adversarial networks have relative to variational autoencoders is that there's no inference network. There's no way of estimating the z coordinates for a given x coordinate. But that's not an intrinsic limitation. You could add an inference network if you want. One particularly interesting thing is you could use a generative adversarial network as the inference network. So you would train two generators and two discriminators. One generator maps from z to x. One discriminator says whether that x sample looks real. The other generator would map from x to z. And then the final discriminator would say whether that z looks realistic for that value of x. And this would allow you to have an arbitrary posterior distribution over your z code, rather than one that takes on a specific parametric form for the variational learning. But no one has made a prolonged attempt to do this. We did experiment with this a little bit at Lisa Lab when we wrote the original generative adversarial networks paper. And one thing that's a little bit difficult about doing it is that your layout in z-space might be very discontinuous. You might have very similar examples occurring from very distant portions of z-space, and that can make your inference problem very multimodal. Another extension that has been done is to learn a conditional model where you provide an extra input y to the generator and also to the discriminator. So this input y can be anything you want, really. In the paper that was written by Mehdi Mirza and Simon at Flickr, they used photos as inputs and sets of semantic tags as outputs. So the idea is that the generator net is given a photo and is also given some noise and is told to generate a tag that goes with that photo. And it can generate many different possible sets of tags that reflect the way that different users would tag the photo. The discriminator net is also given y as well as the x sample, and it's asked to say how likely it was that x was a correct output for y. More recently, Facebook and NYU developed an approach to scale up generative adversarial networks to very large images. As I showed you earlier, generative adversarial networks don't work very well for modeling things like CFAR, and Facebook and NYU got around this problem by designing a Laplacian pyramid. The idea is that you use a generative adversarial network followed by several conditional generative adversarial networks. The first generator outputs a very low resolution image, and then it goes through a sequence of recursively scaling up an image and then adding high resolution details to it. And after going through several stages of scaling up and filling in high resolution details, the final output is a high resolution image. One thing that's different about this setup is each layer is only looking at whether the output of that layer's generator is realistic. So there's no longer a discriminator that says whether an entire image is realistic or not. The samples from these models look very realistic and are very high resolution. This is probably the best generative model of images that's ever been made. And the authors ran some tests where they actually had real human experiment subjects report which images they thought were real or were fake. This kind of evaluation hasn't been done before on neural network generative modeling, as far as I know. So there aren't many baselines to compare to. But one baseline is the standard generative adversarial network baseline, where they found that humans mistake the photos for reality about 10% of the time. Using this Laplacian pyramid approach, they were able to bring up the rate at which humans mistook samples for photos to 40%. On this slide, you can see some examples of photos sampled from the model. In the leftmost column, I'm showing the low-resolution image that's used to kick off the chain. And then the next columns to the right are showing several different high-resolution photos that were sampled by upscaling that one low-resolution photo. And you can see that there's different variation in each of these photos here. So it really is a generative model that can sample different things. There's several open problems with generative adversarial networks, and this is a research conference, so a lot of the purpose of my talk is to get all of you thinking about some of these open problems. I've mentioned all of these earlier in the talk, but I want to recap and focus your attention on some of them. The first of these open problems is to determine whether non-convergence in the game is a serious problem for generative adversarial networks. We know that in general it's possible to design games that have very bad non-convergence properties, but we don't know exactly how bad the non-convergence is for the generative adversarial networks games in particular. We know that if you're able to optimize directly over probability distributions, then there is no non-convergence problem. But we don't understand exactly what the consequences of using specific neural network formulations rather than non-parametric probability distribution formulations are. Secondly, if we are able to determine that non-convergence is a problem, how can we prevent this non-convergence? How can we design optimization algorithms that are intended to find Nash equilibria of games using gradient-based methods? And how can we make optimization algorithms that are more specialized for these problems than just gradient descent? And a third open problem that I want to focus people's attention on is whether there's a better loss function for the generator network. As we've seen, the discriminator network is already doing the same kind of learning that we would expect it to in the maximum likelihood setting, but the generator network is not. There is a reward function that's equivalent to maximum likelihood and expectation, but it has really bad variance. So if someone is able to design a reward function that has a better bias variance trade-off than we have right now, that could improve the quality of the generator quite a lot. That's everything I have for today, so I'm available for questions.